Morning. My name is Roberto Bruschi, and today I'm going to introduce to you a research contribution that the research unit of the University of Genova did in the context of the 6G Twins PRIN project. The contribution is entitled 5G Beyond 5G Network Programmability Platforms and Digital Twin Networks, the 6G Twins Approach. Well, the outline of my presentation is the following. I will touch some introduction and motivation for the work that we have done. Then a very brief outlook on the 5G and beyond 5G technologies. And then we will speak about some monitoring and observability technologies that have been used in our work. Then we will speak about our approach in the digital twin networks. We'll present an interesting prototype that we developed in the second phase of the PRIN project, and that represents somehow the contribution that we had no time to publish in some scientific publication. This is the reason why we selected this work to be the topic of the current presentation. And then we will draw some conclusion and future work. Then, regarding the introduction and the motivation, we know that today 5G and beyond 5G infrastructure, if you want, and technologies, architecture are arising. And we had before the rise of network function virtualization, that today it's a cloud native virtualization. We passed from typical EAS approaches that we had in the first phase of ETSI-MANO, ETSI and FV-MANO, then concepts like network slicing that reinforce the virtualization of network services, and especially vertical application that can be bound to this kind of virtualization containers. We know that there is a strong work within the programmability of this kind of infrastructure, of the technologies that are used, and especially there is a huge contribution in this moment regarding observability approaches that can be used holistically to monitor from the physical infrastructure to any virtualized layer up to the vertical application. Here, the role of the digital twins apply to any layers, but especially on the infrastructure level, on the mental level, might be more than important for a simple reason, because many times we don't know what happened when we try to touch something at the infrastructure level, which is the impact at the level at the higher layers. So at the application layer, at services, in the platform, in the network platform, etc., etc., etc. This might enable to enable a very strong use of artificial intelligence and machine learning, especially in the orchestration management of networks, in order to have an experimental validation and especially to control the energy and the energy consumption of networks and related infrastructures. Regarding the 5G technologies, we might summarize that the new technologies bring to us a multi-layer environment in which we might have multiple stakeholders. On top of this figure, you can see the network application orchestrator. So it's a tool that is orchestrating the life cycle of all the vertical application that might be installed in the edge cloud continuum connected through 5G or beyond 5G technologies. The glue between this orchestrator and the entire virtual physical infrastructure might be the operation support system and the business support system. So these are the interfaces exposed to the final customer, to who is bringing applications into this network. And then we have a level in which we have the network function, the 5G system itself, So all the network function composing the 5G access and the 5G core, so Oran technologies or UPF, AMF, etc., etc., etc. And then we have the level of the infrastructure of the data center. The hardware that is used to create virtual environment where network function, various sets of network functions belonging to various cores or various slices can run. And this is the level of the infrastructure itself. In this presentation, we are going to look especially in this in the programmability of this latter layer. So in the layer of physical devices, of physical data center, or physical network devices. In order to have a digital twin, what we have to do, and this will be used also in another way in this contribution, to test the experimentation of the digital twin that we created somehow, it's very important to have monitoring observability functions. In a 5G system, we might have various functions dedicated to these objectives. So we might have functions that are monitoring the infrastructure level, so the data center level, from the physical level to the level of any containers that is exposed to any of the different tenants that have an access in that data center. Then we have the MDAF, the Management Data Analytics function, that is going to monitor and to observe the performance and the behavior of any network function across its life cycle during the management function itself. And then we have a third well-known function that is the NWDAF, the Network Analytics function, that is a function inside the 5G system that is supposed to collect analytics on the behavior of the 5G system of a specific slice, etc., 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 in terms of performance of the 5G system itself. So in the performance, in terms of bit per second, and over that are performed by UE, etc., etc., etc. So there is a difference between the monitoring and the observability. Monitoring, we know, it's the ability to collect metrics and logs somehow from remote and distributed system, especially to some central location to inject this data to some analytics algorithm that might help to understand some anomalies or to monitor the correct behavior of the system, the efficiency, etc., etc., etc. The observability, it's something different. It's something that might be defined as the ability to measure the internal state of the system only by its external output. So it's a way in which we apply over some monitoring tools some internal models of the system in order to understand, to predict which is the internal state of the system and its correct way of behaving. So somehow we are going to trace the behavior of the system to understand events and to deeply understand what to do with dependency and with the behavior itself of the system. This is a framework that we developed in our lab, in which we are able, especially, to monitor different kind of statistics related to Kubernetes for the network function, but also the energy consumptions of the various processes that are running over the system. So we deployed a number of open source or custom source exporters, software tools, in order to collect all these metrics in a central data series database that is Prometheus. Then we have some network function. Here we have the MDAF, but we have prototypes also of the NWDAF and the IDAF that are collecting the metrics, and they are performing analytics algorithms in order to expose somehow, again, to Prometheus, all the data that have been estimated and pondered. Regarding digital twin network, well, we developed a software that is called Network Convergence Layer. It's, again, it was designed initially as an additional element of the TNT Lab OSS that was used to automate somehow the configuration in the testbed of our laboratory that is composed by multiple switches, multiple routers, firewalls, etc., etc. It's a small-scale network, but with a sophisticated architecture, let me say. It has some core capabilities in the sense that it can access devices through the management interface, so through REST interfaces or SSH. It can retrieve and store the device configuration every time that something is changing. The network CL is able to modify an internal database with all the history of the various configurations that changed. Moreover, the NetCL has also the capability to control the configuration, so to add, delete, modify any elements of the configuration of a firewall, of a switch, etc., etc., etc. It exposed on the north side a number of REST API with an open API specification. How this software is related to digital twins? Well, because we extended it in order to make it able to automatically create in a network emulator well-known like GNS3. It is used by many network engineers in order to have a sort of manual digital twin of the network where to test the various configuration to understand if some certain configuration of the various protocol might work as desired, etc., etc. We extend the network CL in order to read the topology and the configuration of what is managing. It can recreate the entire topology within GNS3. It is able to inject inside every emulated switch the configuration, selecting the correct firmware, software, physical interfaces, etc., etc. It is able to replicate the physical network that is managing over GNS3 to start the network and to start with a what-if analysis. So, for example, for any kind of operation like, I don't know, a firmware upgrade or a complex reconfiguration like the remigration of some virtual routing function or the binding of a VLAN on a secondary path, etc., etc., it is able to test before this sophisticated operation over the digital twin. And if the functional tests that are defined for that operation are successful, only in that case, the NetCL will go for updating the physical twin of the network. So it's reporting the operation because it was successful in the digital version. Well, so the network CL in few words can manage the deployment workflow of the network. It can test and validate a certain configuration, like firmware, software upgrades, virtual routing, migration, firewall security rules. So because we are managing also firewalls, so we can define certain policies, and we might use the digital twin of the network over the GNS3 to do some functional tests to see if the firewall policies are compliant with what defined in absolute. So we are going to complete this work, but here you can see the network CL, for example, in operation. Here you see GNS3. This topology was created directly by the extended network CL. In here, you can see the logs coming from the network cell itself. And here you can see the REST interfaces. In this moment, we are just sending a message to create a new VLAN with VLAN ID 221. The message arrived to the system. We can set a description, a name, etc., etc. Then we can also define where we want to terminate this VLAN over our network. So whenever a VLAN is declared, this is configured in all the switches in our topology, and then it is configured in the correct mode, access mode or trunk mode, only if a termination of the VLAN is somehow defined. Here you can see all the logs that correspond to the fact that NetCL is accessing to every emulated devices in order to add this VLAN. It is interacting through SSH or REST interfaces. And here we are getting, so we are reading which VLAN have been configured. And here you can see the topology, the subtopology for the single VLAN. So where that single VLAN has been configured by the NetRCL. In the next demo, here we are going to add a virtual routing function. Again, the screens still represent GNS3, the logs, and the REST interface where we are sending comments. We are posting, so we are creating a new VRF, called VRF demo live with that description, and with an ID, a route distinguisher, so an identifier of the route itself. That VRF has not been defined before. So now we are getting, okay, we don't have any VRF still now, because the VRF, the virtual routing interface, has no interfaces. So the NetRCL knows that exists a virtual router, but this virtual router has no links. So we don't need to declare it really in a server. Whenever we are creating the first interface of this router, a VLAN interface, at this point, it's configured in our devices. So here you see the VLAN interfaces that have been created, all the data that have been filled by the NetRCL automation, and here you can see for this single VRF all the nodes that are connected in the topology. Well, finalizing, since the emulation of a network like that, it's something computational not negligible from the point of view of the energy consumption, because we are relying on a complete emulation of networking devices. We are completing a work in which we are trying to understand which is the energy consumption in emulating this kind of network, what we can gain, so how more efficient might the network control become, and how much energy and delay we are consuming for that. To do that, we are collecting the energy consumed by the physical network and also by the logical network, while we are synchronizing the data on the topology effect, on the various configuration, on the counters in the interfaces, etc., and which might be the cost in doing different kind of validation on the digital twin. Well, regarding conclusion and future work, we saw a specific contribution coming from the research unit of Genoa to the 6GTWINS project. We developed a digital twin system able to represent network devices with their firmware and to automate the creation of the digital twin itself and to perform even what-if analysis of what is happening. Now we are looking to the cost of having this, understanding how much energy we need to create the digital twin to perform any kind of what-if analysis, and which might be the cost in, let me say, not applying this kind of system and having some network mismatch, or etc., etc., etc. Regarding the future work, we are going to apply some AI-driven network automation, especially we are looking to use the model context protocol in order to make easier for the user to define which kind of tasks the user wants to do on the digital twin, and then which are the conditions to be used in order to assess as positive, as successful the task that the digital twin is doing. And then especially we are going to complete some scientific papers on this with validation and integration results. Thank you for your attention.